Working. My mic. Okay, let's get started. Any questions? Take a roll call. Cauchy concentration, So let's get started. I'd like to finish up on scattering and then move on to some of the integers. This is just the slide I like to show about some of it. It's a very good moment. We actually the most famous achievement of his, I think, is the fact that he mentored 4 students who later won the Nobel Prize with Heisenberg, Cauchy Integration. And he himself never won the Nobel Prize. Okay. But I like to point out to the fact that they did the group some of the models. And most people usually are that the Lorentz model. So instead of thinking to the Lorentz some of the model, to give him credit for what he's done. Okay. So let's get back to something we talked about last time, which is Rayleigh scattering. I like to get over a bit with this quickly. So in Rayleigh scattering, what you do is you do small particle scattering. You get a whole bunch of small particles. Then each of the small particles is going to behave like a Hertzian dipole, because the incident wave produces electric field and current on a small particle, each of which will look like a small dipole. So we reduce it to use our Hertzian dipole again, and we know that the Hertzian dipole can be described by the current distribution such as the point object over here. There's a delta function somewhere which is hidden behind here, actually. Okay, and then you can find the vector potential of the ray delay in those forms, and then the electric field is given by this, and then because we are in the near field, only one of these 2 terms is important. What do you think the important term is? Because the electric potential of the A term is the scalar potential when you see this term is more important. We are very near to the the gradient of the so close to it, near to the 4th point, and then phase derivative is a lot bigger than the time derivative, and then you only keep the scalar potential term, and essentially we can deal with electrostatics when you describe the E field as a negative gradient of the scalar potential. So we can solve this problem if they're very close to the source time, as they have done in your homework, treating it as a Laplace problem or static problem. And once you're able to do this problem, you can actually study amazing things, like understanding why the sunset looks beautiful, why the sky is blue, and why we have the hue of gray so much in the sunset, and so on. So, because we can use electrostatics to study this problem, we can solve this Laplace problem, and we give you the homework when this small particle is produced and is switched upon by an incident field on the left. That incident field is usually used more dipole. And those dipole moments are given by the equation in the top right hand side. One, the first one is the field outside the object. Okay, the other one is the field inside the object. The difference here is that the incident field is anharmonic. So the small dipole reduced is also anharmonic, even though it looks like an electrostatic field. So imagine that if the incident field is anharmonic, there is static dipole that is also oscillating, and the next thing that it does will be so when this thing radiates from anything for a while. So when this dipole oscillates and radiates, that radiated field is called a scatter field. So this is the mechanism of scattering. This radiation of the field that is coming in. Okay. And you solve this problem already, you can actually figure out the dipole moment quite easily. And so you try to match up the potential that you have for a dipole with that you see from this problem. And by matching up the solution, you find that the dipole moment is given by this. I won't go through the details. Okay. So you match up the solution of a dipole with what you have, you can find this scattering amplitude E sub S. Okay, E sub S is essentially given by this expression over here. After you have matched them up together. And so you know the dipole moment, and that if you know a Hertzian dipole, you know that the potential is going to be given like this. And then you know that scatter potential then has to be equal to what we said before, equal to this constant over here, which is what we found previously in this slide, or also in the homework. E naught is essentially E incident. Okay, so you know the amplitude of the dipole moment because you essentially know Q. And then because of that, you can actually find the far field radiation due to this Hertzian dipole now. So now you take the same dipole to the far field, and in the far field, you cannot ignore the vector potential. The fact that the scalar potential does not hold true anymore in the far field. So away from the far field, you have this kind of dipole behavior that we went through class before, and if you assume that this vector potential is a spherical way, then you can actually simplify this far field and it will look something like that. And you can actually work out the E theta in the far field with respect to the incident field. You find it will be given like this. And then you can find the total power scattered by this small dipole. This is called Rayleigh scattering. It was done by Lord Rayleigh many years ago. I don't know if you know Lord Rayleigh. Lived a very comfortable life because he's the Lord. And he had published over 400 papers in the law. And in addition to that, he owned a farm, so he is an unusual man. So you can take this expression, plug into the Poynting vector that you can calculate from that, because you can find the magnetic field very easily using this plane wave approximation. The spherical wave becomes a plane wave. If you know the E field, you can easily find the H field, and hence E cross H, and find the Poynting vector and calculate the power scattered. One thing to note here is that the power scattered is proportional to omega to the fourth power. And if you step back and try to figure out why omega to the fourth power, essentially go back to here, okay? Go back to the fact that the IL, the current moment, is I omega times QL. QL is something proportional to something like this, which is the dipole moment, okay? So the current moment is proportional to frequency. And then you have your E theta, which essentially becomes proportional to omega squared. Let me see if it makes sense to say that here. I'm trying to see if you can find a quick way to explain why omega squared here. I see one omega coming into here. Okay, and then the gradient of P, and then A. Yeah, I couldn't find a quick way to explain why this is omega squared. But the fact that this is omega squared is usually used by physicists to say that radiation is the acceleration. So if the omega squared is the electron acceleration. And the fact that we have this formula that is proportional to omega squared means that the far field is proportional to the acceleration of the electron. Okay, I couldn't find a quick way to explain that, but I think it is accepted out of this concept. So because E field is proportional to omega squared, the energy then is proportional to omega squared power. So there's some of the things that you should notice about radiation due to charges. And because of this power scattered by one single scatter, you can describe a scattering cross-section in this manner, where the incident power density times that area, the scattering cross-section is equal to the power scattered. And by using this definition, you can find the scattering cross-section of the small part. So what this says is that the scattered power is proportional to the force power, which means that the higher the frequency, the more the scattering. And this has a very significant effect because it explains why the sky is blue and why the sunset is gray. For instance, if I look at this picture over here, sun is broad spectrum light is produced by the Hawk frequency, but when the light is scattered out the atmosphere, it's almost very much more part of the scattering. High frequency scattering is small than low frequency scattering. So the blue spectrum is quite large, scattered more. So if you look up into the atmosphere, you mainly see scattered light. And because you mainly see scattered light in the sky, so it's blue. So that explains to you why the sky is blue. Because you are essentially seeing the scattered light spectrum. However, if you are in the sunset time, the light has to go through a thick atmosphere. And by the time the sun reaches your eyes, again, maybe not that nicely drawn, maybe this other picture is more nicely drawn. Now this, you can explain why the sunset goes. The blue light has been taken out of the spectrum, and by the time the light spectrum equals to eye, it becomes dark. Okay. And then there's another interesting thing about using light for navigation. The thing about light is randomly polarized as it comes from the outer space. And when it induces the molecule, the light increases the molecule in vertical or horizontal. It is vertically polarized, so it induces the dipole. And you probably remember that the dipole radius is a radiation pattern of the donut. So if it's directly below the dipole, and it is vertically polarized, you don't see radiation from this dipole. So if it's directly below this dipole, you see mainly radiation from horizontal dipole. You see that. And then by looking at the polarization of the light, you know where the sun is, whether it's above you or whether it's coming from the horizon or that direction. And that's the what is the use of the light direction and the field across the light use the coming from the sun to look at the polarization of light. There is the sun. So this is the sunstone. I don't know very much about it. Another thing that is important is the fact that rays, that's the of small scattering. And the scatter becomes thicker and not over the scatter. And now the thing that the dipole that is used on the small particles is the dipole. We find that as you increase the frequency of the electromagnetic wave, the scattering cross-section will look something like this. It increases the frequency, which is the horizontal axis, and then it will go up and settle and come down. And the asymptote, this is called asymptote. Asymptote is something like this. Cross-section area of the atmosphere will be 5A squared. When you look at it, cross-section essentially just becomes pi A squared. What it says is that if you look at it very small in the spherical particle, you will have a certain cross-section very similar to the cross-section area. Because in order to predict the rest of the certain cross-section, that you have to do more with the theory. And that we don't have time to get into. Takes quite a bit of mathematics to solve that problem fully. It's written up in many textbooks as well as textbooks that have written. Another very interesting phenomenon of scattering is that if you have a small particle, when the frequency is low, the wavelength is long, this dipole scatters almost isotropic, like a donut, except for the no. However, if you increase the frequency, you find that it scatters gradually more and more in the forward direction. As the frequency gets higher, it scatters in the forward direction more and more. And that is very constant increase in many students. And very, very constant increase in many students, because many students will think that if I have a particle, if I increase the frequency, most of the scattered light will come back at me. But that is not the correct intuition. The intuition is that the light gets scattered into the forward direction. And as students who do calculations to say, don't understand what and the electromagnetic wave scatters to dominate the forward direction. There is a physical reason for that. The physical reason being that if you look at the scattering at high frequency, at low frequency it scatters like this, but high frequency, the scattering solution has to form a shadow behind the object. In order for this to form a shadow, the scattered field, there is an incident field that comes in. Incident field is everywhere. But in order for it to form a shadow, the scattered field has to cancel the forward direction. You see that? Incident field has to cancel the scattered field in forward direction on the shadow in order to come up with the correct. So you calculate the scattering cross-section of this, you find that mainly scatters in the forward direction. Okay. You get this? You get this? That the scattered field has to cancel the incident field in the forward direction to form this shadow, which is something that the metrical optics will tell you. The metrical optics tells you that when the frequency gets higher, it will tend to forward scatter more. And there's another amazing theorem called the Optical Theorem, which says that if you know the forward scattering of an object, only use forward scattering directly, you know the scattering cross-section of this object. So that is called optical theorem. Too hard to prove it. And it's valid for all frequencies, not only optics, but even microwave. Knowing the forward scattering quantity of the scatter tells you what the scattering cross-section. It's a very powerful and amazing theorem. And they like to actually attribute it to mode orthogonality and power orthogonality that we never study in the waveguide. It turns out that we studied mode orthogonality sort of, but we never studied power orthogonality. So if you have two fields, then you might have a field consisting of two fields, A1 plus A2, and these two fields are orthogonal to each other, then very simply speaking, if I were to take the square of this, it will be roughly this one, dot with A1 plus A2 complex conjugate. And if you multiply this out, it will be A1 amplitude square plus A2 amplitude square plus A1 dot A2 conjugate plus A2 dot A1 conjugate. So in linear algebra, we know that if two quantities are orthogonal, this term will disappear, this term will disappear in linear algebra. But if you go to abstract Hilbert-based algebra, these two terms will also disappear. So when you have mode orthogonality that we sort of alluded to in the photo, you will have power orthogonality. So this will be power. This will be power, this will be power, which means that each mode itself carries their own power independently of each other as a wayside property. So what it means is that each ray is going to carry their own power independent of the other ray. Because this same way are orthogonal to each other. And as a result, two rays are independent of each other unless they are propagating in the direction. If they are propagating in the direction, then they are not power orthogonal. So you can use this kind of argument to arrive at the optical theorem. Let me use the rest of the time to talk about Thermophil integral. Okay, as I said before, I told you about Thermophil, a very notable man who had 4 students winning Nobel Prizes, but he himself did not. He did his group Thermophil model, so I call it the group Lorentz Thermophil model. So are there any questions before we move on to talking about Thermophil integral? Yes. Oh yes, yes. I glossed over that. I say as the frequency gets higher, you have to use mean scattering to study this part of the spectrum. No, color is due to a different thing. Like, why does something look green? Or look green because it reflects mainly the green part of the optical or the visible spectrum. So it's very much due to the chemicals, the emulsion, whatever you have in the thing. So if you put certain kind of emulsion in the thing, it is a dot. All the other spectrum, but only reflects the green color, then the thing will look green. Essentially, it's due to microscopic, it's due to quantum theory, because each molecule has a resonance frequency. So if you have this molecule and you drop one at a certain frequency, it will take away the spectrum. So the drop the spectrum will leaving the other section behind. Okay. So you not use really mean scattering to explain color. Mean scattering can explain things like this as to why the cross section of a particle becomes by A squared. But doesn't explain why certain things of different colors. Well, I guess roughly we know. Artists know that why the color and I think the RGB concept, red, green, and blue concept, actually came about before quantum theory. Because there, well, with light and theater, the 3 primary colors of the light, which is RGB. But actually, RGB theory is very little to do with quantum theory. It's mainly to do with the perception of the human eye. You see a certain RGB, I will see a certain RGB. Every individual will see a different RGB. And so we all see colors differently before. So color is a psychological. Well, I think all of us see different colors before this. It is the property of the material, but if the material is made of light, it's supposed to see the light differently. But we all are human beings, so we almost see the same color. So a dog may not see the same color as you do. A monkey may not see the same color as you do, right? There's no way of telling that it's not possible. So, color is due to the perception in the eyes. Of course, we talk about rock forms in the eyes as you make yourself the items perception and so on. It's not more complicated subject. We have something to do with biology, human psychology, and the property of life. Okay, and painters have their own set of primary colors, which is red, yellow, and blue, right? Painters use that three colors in all colors in the world. But intelligence when they design use red, green, and blue. They're all colors. And the reason for that is because painters are talking about reflection and reflection of light. Because there is television work as it can do. Okay, it's not a very simple subject to talk about. Okay, any other questions on scattering? Well, scattering is, as you know, extremely important for sensing. Even though we're not seeing microwave frequencies, we have radiometers that detect microwave radiation from the earth. So you probably have seen more sensing of the earth frequencies, even the microwave frequencies. And if you can make the picture large enough, you can have pretty good resolution of the image of the earth and microwave frequencies. The fact that in order to get high resolution picture of something, you have to have a picture. And if you have a big picture, but you could buy a very big camera with a big lens, the resolution is better. I think you will see the physics later on when you study some of them. If you have a camera with a small aperture, it will have very poor resolution. So let's look at the mathematics behind the point source. Okay, that if you have a point source, how do we solve this problem in closed form? So we know that if you have a point source, it generates a spherical wave. That is what we know. And it generates a spherical wave in closed form. Okay, I'm going to switch over to the optics notation. Because in optics, we like to write spherical waves. This is going to be high and frequency. I will switch over to this kind of notation. So we have to do a cultural shift in terms of this kind of thing. And spherical waves are not that simple to deal with, because we know how to study the reflection of plane wave by a single interface, but we do not know how to study this reflection of the spherical wave by this single interface. In fact, approximately, we know how to do that approximately. So let's see how we can do this by doing mathematics. And this problem was solved by Thermophil around 1909. Okay. And the key thing is that we have to solve this problem first, which is that if I have this problem, which is essentially the green function problem, a point source on the right-hand side, Okay. If we have this problem, essentially I want to find the green function. We have learned how to find the green function anyway. We have to long for this that substitution using different there. So we could do an entirely different way of finding this green function by using Fourier transform. Okay. And using Fourier transform will give us different insights into what a green function is. So I'm going to assume that this green function can be Fourier transform, and hence it can be written as a 3D Fourier transform. And if I write out this 3D Fourier transform, it will look something like this. And then its Fourier transform in the Fourier transform variable. Okay, this is just a statement of Fourier transform in 3 dimensions. We all have seen 1D Fourier transform very much over and over again in electrical engineering. We just have to change this to a 3-dimensional Fourier transform. So Fourier transform the X variable, Y variable, and Z variable. If you do that 3 times over, you get this expression. Can you see that? Okay. And everybody sees it. This is just rewriting a 1D Fourier transform 3 times. Say if I have a just 1D function, and everybody knows this. As an electrical engineer, at least as a good electrical engineer, you should know this, right? Because you've seen that in Untitled. In electrical engineering, you don't emphasize Fourier transform in the space. Now, in solving network equations, you have to emphasize the Fourier transform in the space domain. If you write 3 times over, you get the second last one. Okay. And so you know, when can you do things like this, writing something in terms of its Fourier transform? When can you do that? Any good hypothesis around? When can you present the function with its Fourier transform? What is the criteria? Yes. When you got linear time invariant, that's correct. Yeah. Say something more stricter than that. Can you say something stricter than that? It's also correct, but it's not as strict. Say something that sounds like a mathematician. No, periodic note is not required. You have some. I was going to say, not really. Not really. Yes. Fine, that's almost correct. Okay. The requirement for this to be true is that if something is Fourier transformable, it's not energy, okay? If it is absolutely integrable, something that you should learn from this course. Okay, something is absolutely integrable, not finite energy, but if you take the absolute function of this function and integrate it, and if you can be integrated, the Fourier transform this. I can prove it by going to 10 times proving this one. You can read the lecture note. Lesson you read the lecture note, you can solve it. Why we need absolute integrability or Fourier transform this. So let's assume that this function is absolutely integrable. Then we can write it in this manner. And then the next thing we do then is to plug this into the above equation. Okay, plug this Fourier expansion, not this Fourier expansion, but plug this Fourier expansion into the above equation. And then exchange the order of integration and differentiate. When I plug it into above like this, you the basic operation and Laplacian. I want to take the Laplacian into the integral. And that is not allowed in mathematics unless the integral converges after the exchange of the integration and differentiation. Don't do that unless you get convergence. Let's assume that convergence is there. Plug into the first line, I change the order of integration and differentiation. And you recall that these things look like plane waves. They're not actually plane waves, but what you have then is that the Laplacian in the coordinate space is given by this. And in the Fourier space, after you plug it into the thing, it would just become minus kx squared minus ky squared minus kz squared. If we exchange the order of integration and differentiation, and now let the Laplacian operator operate from those same wave-like functions, the Laplacian becomes that. Can you see that? Can you see that? Can you see that? No? Okay, let me go a bit slower then. So I have this integral. Okay, it has two terms, x, y, z, and I expand this in terms of a Fourier transform. And then I've changed the order of differentiation and integration so that I write this decay as dkx, dky, dkz, and then I have Laplacian squared plus k naught squared. Let me call this k naught squared. B tilde k e to the I k dot r. This is just a shorthand notation for this complicated looking exponent up here. Okay, I just replace that with a shorthand notation, and I'm going to use this a shorthand notation for that. This I'm just going to say is decay. Okay, can you see this start? Okay, now I let the Laplacian operate on the integral. The only place that depends on space is the e to the ik dot r, and you see that. And those are plane waves. And the Laplacian will just become that. Good. Excellent. So then what I have then is that the left-hand side will be this with decay, and this will be k squared. Sorry, k squared. K squared is this one, okay? Plus k naught squared. E tilde k bar e to the ik dot r. So that will be the left-hand side. The right-hand side will be this thing over here. The right-hand side will be this, and I can write the right-hand side. This is left-hand side. Right-hand side, I want to write it in a similar way using Fourier transform. And if I write it 3 times over, when you see that the right-hand side can be just written in this manner. It's a 3D Fourier transform with it. E to the ik dot r repeated 3 times. Okay, can you see that? Okay, now I can equate the left-hand side and right-hand side. Okay, equate the left-hand side, right-hand side, and claim that these two integrals are equal to each other. So I assume that these Fourier transforms exist and that they are equal to each other. Okay, when two functions are equal to each other, the Fourier transforms are also equal to each other. Does that make sense? The two functions are equal to each other. If the left-hand side equals the right-hand side, the Fourier transform must be equal to each other. So I can say that the integrand must be equal to each other. Okay, everything is kosher. Okay, there's no cheating here. Okay, so I can equate the integrand and come up with an equation that V tilde K is equal to the other one. Okay, I have a minus sign somewhere. One over K naught squared minus K squared, which is essentially KX squared minus KY squared minus KZ squared. Okay, this is just K squared. So I found a closed form solution for this problem in the Fourier space. Okay, then I can get the other solution in the coordinate space by an inverse Fourier transform. If I use the shorthand notation, then I inverse Fourier transform this quantity 3 times. Again, use dk to mean dkx, dky, dkz. And then I write the inverse Fourier transform corner. Okay, will be k naught squared minus kx squared minus ky squared minus kz squared with a minus sign out front. Everybody got it so far? Very good. Everybody gets it. So the key now is how can we invert or evaluate this integration in closed form? That is the challenging part. You probably never came across this integral before. Okay, but you're seeing it now. And it will be very enlightening to see how we can evaluate this integral and see the physics coming out of it. So you can see some kind of physics, but not quite real physics. Because you say, oh, this looks like a plane wave. Is this really a plane wave? It is not truly a plane wave because in a plane wave, kx squared, ky squared, k squared must add up to a constant. But for this exponential function, they don't add up to a constant. The constant is not determined. So it's not truly a physics problem, but let's see if we can invert this integral. So let me rewrite that thing which we have already solved many times over using different methods in this course. We found the green function to be this. But what it says is that it is going to be equal to 1 over 2 pi cubed, a triple integral. Let me put 2 of the integrals on the outermost integration. Okay, put 2 of the integrals in the outermost side, and then put 1 in the innermost integration, so that I have a much simpler problem to address. Okay, and I ask myself if I know how to evaluate the innermost integration. Okay, can you see this innermost integration and see if I know how to evaluate the innermost integration? Can you see what I've done? I just put 2 of the integrations outside and put 1 innermost one in the inside. Okay. So if I know how to evaluate this integration, bingo, I'm halfway there. This is a simple enough problem for us to think about. You might even have encountered this problem before. Do I know how to invert this Fourier integration? Okay. So one of the very popular technique in Fourier transform is to use Cauchy integration. And we see if we can use Cauchy integration technique to evaluate this integral. And this integral is in terms of the kz variable. Can you see any pole in the integral? If you think kz is my variable. Kx fixed, ky is fixed, k naught squared is fixed. Can you see a pole there in the integrand? Okay, I see some nodding head. You look at the integrand in the kz variable alone, it has a pole, and that pole is given to be and kz equal to k0 squared minus kx squared minus ky squared. But I'm keeping kx and ky fixed. I'm just very intending on doing the kz integration only. Okay, only the kz integration. I see this pole there. And then Cauchy integration technique comes to my mind. Okay, then I look at this and see, well, if I look at the kz plane, it looks something like that. It has a pole at this location and another one at this location. I'm intending to integrate this Fourier transform on the real kz variable. Okay, how many of you have not had a complex variable before you come to this pole? You don't have. Okay, there's something called the Cauchy integration technique. It says that if you were to integrate something, an analytic function, okay, if the function is analytic, say if this function is analytic, then this function can be integrated in terms of the poles of the system. Okay, say if this function can be written like this. Okay, it has a pole at z0. And if you were to integrate it along this contour C, and this is a pole there, and then the integration of this function in the circle, in the contour, is the same as evaluating the integral around the pole, only that called the residue the pole. Okay, if you have had a course in complex variables, this is a bit of picture. If it's not, then how can I motivate this? You can think of a pole as almost like a point force in Laplace equation. Okay, and if you integrate the field around the point force, only the integration around the point force that is very close to extremity is important. Okay, but in the proven, I'm not going to prove it. This is called Cauchy integration technique. So what you can show is that integration on the real axis is the same as integration on the real axis plus this C integration on the contour. Okay, not exactly, but what you can show is that if the integration on C is equal to 0, okay, if you try to integrate this function, and you can show that when you try to integrate on C, it contributes to 0. It means that you can add integration to your integration. It's abandoned because it is 0. So I can say that integration along the real axis is the same as integration around the circle. So this part does not contribute to anything. And Cauchy's theorem then says that integration around the circle is the same as integration around the pole that you find. Okay. So if you do that, then you can say that this whole integration along the real axis is equivalent to integration around the pole. That is called finding the residue of the pole. Okay. And if you can prove that this integration is 0, in fact, you can prove that it goes to 0 because when kz goes to infinity, this integrand becomes very small. And when kz becomes pure imaginary up here, this exponential function is also very small, making the contribution of this integration going to 0. And so the thing that you need to do then is to actually evaluate this integration around the pole location. You can reduce this to a circular integration like this. And if you do it properly, this integration can be done in closed form. It's called finding the residue of the pole. And then you can see that Pxy is equal to 1 over 2 pi square. Okay. Only a double integral is left. Okay, only a double integral is left. And then you will have to evaluate this one. This one is still there. This kx x plus ky y is still there. And then you have to evaluate this at the pole location. Okay, if you do that at the pole location, you will get something like ikz prime z. Okay, and then you will have this evaluation coming to kz prime. The kz prime is equal to k0 squared minus kx squared minus ky squared. So kz prime is the value of kz right at the pole location. Is what you say. The kz is given by that value right at the pole location. And if you set your kz to be equal to kz prime, you're essentially just integrating around the pole location. And the integration will be done in closed form, and you have only a double integral left instead of a triple integral. So that is a big hurrah for us because we reduce a triple integral into a double integral. Okay. And you can do the same thing when z is negative, and you can detour downward and convince yourself that the contribution from this contour is equal to 0. Okay, this contribution is equal to 0 for z larger than 0. And you can also convince yourself that this contribution is 0 when z is less than 0. Okay. So for z larger than 0 and z less than 0, you can pick up the pole locations differently. And you arrive at this very important identity, which is called the Weyl identity, that the spherical wave can be written as e to the I k r over r, or 4 pi r over r, is equal to 1 over 2 pi cubed square dkx dky e to the I k x x plus I k y y over kz prime e to the I k z prime z. Okay, since it can be done for both positive and negative z, and that let's see if you can see some physical meaning out of this mathematical expression. Okay. So you see this wave here. Okay. You have kx and kyy. What do you see here in this first two terms of the expression? What do you see there? This exponential kxx, exponential kyy. What do you see in your mind when you look at that expression? The time point you want to find. Just the same way, right? Everybody gets that. It's just the same way, and you're doing integration over all kx and ky values. So you are actually summing over all possible plane waves, different wave numbers propagating in the x and y direction. Can you see that? Okay. And then there's the third term, which is this term over here. Before we did this residue integration, we had this kx squared plus ky squared plus kz squared not being equal to anything But now this thing has to add up to k naught squared, because you remember that kz prime is k naught squared minus kx squared minus ky squared. Okay, kz prime is going to be that. Now this plane wave is physical. The kz that is associated with this plane wave is that of a physical plane wave, because this plane wave satisfies the distortion relationship. Can you see that? So this is something very important. And what else that is very important? What else that is very important is the fact that, well, because of this fact, okay, you can define a circle in the kx and ky plane. Okay, you can find this circle. The radius of this circle is k naught. And if you kx and ky are inside this circle, then kz is real. It's so real. Can you see that? If kx and ky are outside this circle, kz becomes pure imaginary. Can you see that? Okay. So when kz becomes pure imaginary, what kind of wave do you call it? Evanescent wave. So very good. So what you see is that outside this circle, you have evanescent spectrum. Inside here, you have propagating spectrum. Can you see that? So this physics is very important. It says that if you have a point source, and if it produces the field, the evanescent spectrum essentially makes the field unmeasurable. So when kx and ky values are large, okay, over here, for instance, to you, what do they correspond to? When kx and ky values are large, what do they correspond to? If you take a Fourier transform, this is essentially the Fourier transform integration. What does large kx and large ky mean to you? If you look at the Fourier transform integral, two-dimensional Fourier transform integral, what does large kx and large ky mean to you? Just like me. You what? Yeah, that's true. That wave will be evanescent, but which means that this wave becomes evanescent in the z direction, which is the correct thing to say. There should be a plus sign here. Okay. But what else does large kx and large ky mean to you in a 2D Fourier transform? Very good. Okay. What you are looking at is the high frequency spectrum of the integral. And if you look at the high frequency spectrum of the integral, it must correspond to the high frequency part of the spectrum, which actually corresponds to the singularity of the green function. Which means that if you are away from the source point, if you make z not being zero, you are away from the source point, you find that the evanescent spectrum is merely cut off. If you make z equal to 0, you're very close to the source point now, the same coplanar point with the source point. You see a very broad band integral. Can you see that? Okay. So the spectrum of this integral changes as you change your z. Okay. So which means that the high frequency information of the point source is lost the moment you move away from the z equal to 0 point. So in essence, super resolution is lost. Because super resolution is lost. So if you have a source point, knowing this physics better now, maybe you can talk about the kind of thing that we alluded to earlier. That is, if you have a source point, you can think of it as being emanating plane wave in all directions, but as the wavelength gets too short in this direction, the wave becomes evanescent in this direction, which means that if you were to put your observation point over here, you only see the low frequency part of the spectrum. You cannot see the high frequency part of the spectrum, because the high frequency part of the spectrum will be out due to the evanescent wave. Okay, due to the evanescent wave. So if you have a point source, if you have this propagating wave coming out of this point source, okay, if you have a good camera, you want the camera to have a long length. And if your camera is good, you can capture the sharpness of this point source very well. In order to capture the sharpness of this point source, you want to make the lens bigger. Can you see that? If I make my lens bigger, I capture more high frequency spectrum, and hence I can reconstruct this fineness of the point source. However, if I have a very small lens, I will only capture the low frequency part of this spectrum. This picture indicated here. Okay, I will only capture the low frequency part and hence not the high frequency spectrum. So this is in a sense related to photography. You should buy a camera with a large lens in order to get the high resolution image of the thing. Just because of this integration. You can think of all light sources as been due to point sources. And this will explain why you can get the high resolution thing. Another very important thing is that we know how to expand the field due to a point source in terms of plane wave now. You see this picture of point source not being a spherical wave anymore, but summations of plane wave. But we already know how to study reflection and transmission of plane wave in layer medium. Agree? So if you look at every component of this integrand, it is a plane wave of some sort. We know how to bounce this plane wave of a layer medium. You already did that in your chapters on layer medium transmission lines and so on. Okay, so solving this problem is just an added complication of taking every component of the plane wave to bounce it off this layer medium. Then you have this problem solved. And some of you did that around 1909. Okay. Any questions on this? So the rest is just mathematics. Take a point source, expand it in terms of plane wave, and then take every component of this plane wave and bounce it off this layer medium. You have the problem solved. Okay, can you see the mechanism here? Okay. So the key here is that we know how to solve for the reflection and transmission of TE and TM waves through a layered medium, agree? Okay, once we have TE waves and TM waves, we know how to solve for the transmission. So the key thing is that if I give you a point source, how do I extract the TE and TM spectrum? So I know that if I have a point source like a Higgs dipole, that the electric field can be written as such. This is Higgs dipole polarized in the alpha direction. This is just a Green's function. And this is the field due to a point source. But I don't see any TE and TM waves there. I do not know how to bounce these waves of a layered medium. So I want to extract the TE wave in this point source and the TM waves in this point source. Okay. So what I need to do next is actually to extract the Z component of this field, because if EZ is not equal to 0, HZ equal to 0, what kind of wave is it? In the layered medium, it is same plane wave. let's think in terms of this spherical. You have this EZ not equal to 0, HZ equal to 0. TM variables. Okay, this is the TM wave. Okay, and then if you have the other one, it will be TE, but there's no TE wave for this source, it turns out. Okay. And hence you can actually go about expressing this thing in terms of real identity allows you to explain this in terms of plane waves. And then it turns out that there's one other thing that you can do, which is that if you have this real identity that we derived earlier, okay, it turns out that you can also express this integration, which is in Cartesian coordinates, in cylindrical coordinates. Okay, and if you express this integration in terms of cylindrical coordinate system, it becomes a lot simpler. I'm not going to go through that derivation, but saying that if I were to apply a transform to this cylindrical coordinate system, then I can show that this very complicated 2D integration just becomes a 1D integration in terms of the k rho variable. Okay, k rho over kz, and then j0, which is your Bessel function that you have learned before. Then you have a same wave in the z direction. Okay, this is called the Thermophil identity. Okay, so the good thing about this identity is that it only has one integration variable instead of two. If you use the real identity, it's very intuitive, that is in terms of plane waves. But if you use the Thermophil identity, it's in terms of cylindrical waves. Because cylindrical waves in the rho direction and the plane waves in the z direction. Okay. So you can get here if you go through the math by doing a coordinate change of variables. Okay. And then you can take this plane wave and bounce it off a layered medium very easily too. And get the solution when you put a point source on top of a layered medium. And after you bounce this wave off a layered medium, it becomes very, very complicated. Okay, the reflected wave might look very complicated. And let me look at some of this integration. Okay. And it might look something like this. Say if I look at E1z, the reflected waveform, it might just consist of I can use real identity and say that it just consists of a summation of plane waves in the kx and ky plane. In medium 1, okay, I'm putting myself in medium 1. And then there might be some reflection coefficient involved because these are the TM reflection coefficient. Okay, e to the I k1zz. Because this is a wave that bounces off. It bounces off with the TM reflection coefficient. It looks something like that. Okay. In general, a Thermophil integral will look something like this. And I can call this complicated integration fkx and fk1. And it does not offer you much deeper insight into this Thermophil integral unless you do something. Unless you know how to make an approximation to this integration. And that approximation method is called the stationary phase method. And that works when x, y, and z are long. So let's see how we can approximate this integral when x is very long, y is very long, and z is very long. Okay, can you see that? When this happens, what happens? If this is the case, can you see the fact that K1z, let me remind you what K1z is again. K1z is square root of K1 squared minus Kx squared minus Ky squared. Can you see that when x is very large, if I were to change Kx a little bit, the base of the integrand will change by quite a bit. Okay. So again, if y is very large, if I were to change Ky a little bit, the base of the integrand is going to change very much. Again, if I make Kz very large, if I were to change K1z a little bit, the base of the integrand again is going to change very much. But K1z is dependent on Kx and Ky through that complicated expression over there. So what it means is that if I change Kx or Ky by a little bit, the base of e to the I to 1 zz also change rapidly. So this gives me a chance to do something creative. Okay, so what it says is that if I look at the integrand as a function of Kx, for instance, okay, the integrand, let me call this integrand. It is going to change very, very quickly when these things become very large. Agree? It's going to be rapidly varying as a function of Kx or Ky, and so on, and so on. So except for the case when the phase of the function is stationary. Stationary means that it is having zero derivative. Then the phase change will slow down. And if you are away from the stationary phase point, the phase of the integrand is going to change rapidly again. Do you catch this point? You see, this three together, Kx, Ky, and K1z, is a rather complicated function. And you can take a point, Kx and Ky, such that the phase variation will be minimal. That is called the stationary phase point. And I indicate the stationary phase point to be that point over here. Okay, that point is my stationary phase point. Maybe this is Kxs. Okay, so do you see the fact that if I were to do a numerical integration, most of my contributions will come from around the stationary phase point? Okay, because if I integrate over the rest of the integrand, it will just cancel destructively. Only the integration around the phase point matters. So in this manner, this function is behaving almost like a delta function. Remember, a delta function, you multiply a delta function with another function and integrate, you only need to worry about the delta function where it peaks to be a very large number. So this point, stationary phase point, is acting almost like a delta function, having its shifting property. So I can take the whole integrand and approximate it with its value around this stationary phase point and take it outside the integrand. Okay, take it outside the integrand and then approximate the integration with a stationary phase point approximation and get a closed form approximate solution. Okay. It turns out that this stationary phase point has a close cousin that we just talked about. Okay, we pick Kx, Ky values so that the phase is stationary. And what does that remind you of? Phase matching. Phase matching is one possibility. What else did you learn recently? That you want the phase to be stationary. Remember Fermat's principle? Fermat's principle says that we find the path of minimum phase. Okay, Fermat's principle is such that when the plane wave goes between 2 points, the phase is minimal. Okay, And that is the point where you have the correct solution. And this stationary phase point also says that if I were to pick the value of kx and ky and kz such that the three functions in combination give a stationary phase to me, then that has to be the correct solution. And that is the point that contributes most to the integral. And as such, you can approximate this very complicated looking integral using the fitting property of this stationary phase point. Just like the other function, it can obtain an approximate solution to this integral. Okay, I'll let you read about them in the lecture notes. Okay. Here's a picture actually, but show the stationary phase point and how it varies and so on.
Would you mind citing the physical property of
Okay, some students don't ask for signatures, but some do.
Yeah, the office says they prefer to get a physical copy.
Okay. Do I need to fill in anything? Okay, good.
Thank you.
You're welcome. Thanks for coming. So, Muna, you want to see me today or? Okay, maybe later about 3:15. I take a break and then.
Okay, where do I meet you?
You can meet me at my office.
Sure.
Okay, I'll see you there. No, that's fine. Okay, there you go.